In this video, we are going to find all positive integers n such that n squared divides 3 to the power n plus 1. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. To find all possible values of n, I'm going to consider the smallest prime number that divides this number n. I'll call that p. Then we can say that this p, and in particular p squared, will also divide 3 to the power n plus 1. So we can say 3 to the power n plus 1 is congruent to 0 mod p, which means 3 to the power n is congruent to minus 1 mod p. And if we square both sides, then we have 3 to the power 2n is congruent to 1 mod p. At the same time, there is also a result that is related to powers congruent to 1 mod p, which is the Fermat's little theorem, which says if p is not divisible by 3, which means p is not equal to 3, then 3 to the power p minus 1 is also congruent to 1 mod p. But of course we know that p is not equal to 3 because otherwise we can't have the other congruence on another power, which is also congruent to 1 mod p. So that means we have two congruence equations altogether, two different powers of 3 that are both congruent to 1 mod p. Now at this point, I'm going to consider a natural number, I call it d, which is the smallest natural number such that three to the power of that number is congruent to 1 mod p, which means like if I have a sequence of powers of 3 starting from 3 to the power 1, 3, 9, 27, and so on, this power 3 to the power d would be the first one that's congruent to 1 mod p, and we can imagine that 3 to the power p minus 1 and hence 3 to the power 2n would be the terms even further, which are also congruent to 1 mod p. Now the importance of this is that if I have this d, like assuming this d really exists, then I can look at this sequence like 3 to the power 1, 3 to the power 2, all the way up to 3 to the power d. This is the first term that is congruent to 1 mod p. And if we do mod p, then for the terms afterwards, 3 to the power d plus 1, then the sequence will start again. Say 3, 9, etc. and then 1. So the next one would be 3, 9 again. Then we can actually interpret this part of the sequence as a block, and then for the powers afterwards, it's just repetitions of this block. In other words, we can say that this d is a factor of p minus 1 and also at the same time a factor of 2n, because those two terms would also be n of some blocks at some point in the middle of the sequence, but after 3 to the power d appears. So d divides p minus 1 and d divides 2n, and what's more is that this d is in fact the greatest common divisor of 2n and p minus 1, which can be justified with the help of the Euclidean algorithm. I can divide, say, 2n by p minus 1, assuming that 2n is the larger number, and then the remainder as the exponent would also give 1 mod p. We can repeat this and explain why d is actually their greatest common divisor. Now, given this, we can take a look at the prime factors of p minus 1 and 2n. Under our assumption that p is the smallest prime factor, p is the smallest prime factor, p minus 1 will not contain any prime factor that also divides n, because p minus 1 itself is even smaller than p. So the only possible common divisors will be 1 or 2. But regardless, we can also say that this p divides 3 squared minus 1, like p dividing 3 to the power 1 minus 1 and p dividing 3 to the power 2 minus 1 would also give the same results, which is that p equals 2, because 3 squared minus 1 is 8, a perfect power of 2. So the only possible prime number that divides it is 2. Now using this, I can go back to the original condition, which is that p squared divides 3 to the power n plus 1. So therefore, 4 divides 3 to the power n plus 1. However, this implies that 3 to the power n is congruent to minus 1 mod 4. Minus 1 all to the power n is congruent to minus 1 mod 4. So that means n has to be odd, but 2 divides n. So here we actually have a contradiction. But the question is, what did it contradict? By looking at all our steps above, we didn't assume anything, we just let p be the smallest prime factor of n, but in fact, this is already an assumption, which we have assumed that n has a prime factor, and so we can choose the smallest one. But it actually contradicted this assumption, which means n doesn't even have a prime factor. So the only possible value for n is that n equals 1. And we can check. Indeed, 1 squared is 1, divides 3 to the power 1 plus 1. So this is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.